Okay, looking at some more examples of horizontal circular motion. So this one, we're imagining there's an aircraft, and it is turning. Its altitude's not changing, not going up, not going down. It's just turning. It's banking to one side, and it's making a turn as a result of those wings being banked. So imagine the plane has those wings. Okay, and it's turning, it's flying off to, in this instance, to the left. Now, the way planes work is the wings create lift. Okay, and it is the lift as a result of the air going over the top of the wing is going effectively slower than it has to travel further, so it has to go faster to move the same distance as the air going underneath the wing, and that creates less pressure above than below. That causes the lift to occur. Anyway, we're not worrying ourselves about aerodynamics, but we're appreciating there is a lift. Okay, big fat L there. Okay, and that is at an angle that is going to equal to whatever bank angle that plane is making. The mass of the plane still acts vertically down, and in this case it's 4 tons. That's 4,000 kilos. So we need to now look at what is happening in terms of this motion. Again, because it's not going up or down, its altitude isn't changing, we can appreciate that the force going up is going to equal to the force going down, and then the result of the overall net force acting to the left in this instance, in order for the plane to bank to the left, that will be your centripetal force. So let's look at our alpha and work this through. So it tells us the angle of bank is inverse tan of 1/4 with the vertical. So tangent is opposite over adjacent. So opposite is 1 for adjacent of 4. And if we want to work out our hypotenuse, we have to do the square root of 4 squared plus 1 squared. So we end up with our hypotenuse being root 17. So if the tan of alpha is 1/4, then we have the sine of alpha being equal to 1 over root 17, and the cosine of the angle is going to be 4 over the square root of 17. So we can now use those two ratios to be able to work on our forces. So yet again, horizontally, we appreciate that what forces going up is going to equal forces going down. So the adjacent to alpha is going to be cos, so L cos alpha is going to have to equal to the force acting down, which is 4,000 G. So cos alpha is 4 over root 17. And as a result of that, we can come up with an expression for L. L is going to equal to 4,000 G multiplied by the square root of 17 divided by 4. That works out in basic terms. Now we can put the G on the end, or we can put it in between. So 1000 root 17, lots of G. Sometimes people put the G in between the 1000 and the root square root. So the square root is the last thing in the expression. But anyway, the force that is occurring, the lift that is occurring, is whatever 1000 root 17 multiplied by G is, which for the record is a number 40,406 newtons, to the nearest whole number. So that is the lift. Now we want to work out the linear speed. So what is the speed, the linear speed of the plane? So we're now going to look at the horizontal component of that lift, because that lift is perpendicular to the wings. So there is a horizontal component of that lift, Okay, so L sine alpha is going to be that force acting towards the center of the circular motion, and that is going to equal to, now we could use mr omega squared, but here we're asked for the linear speed, so that's our tangential velocity, so we're going to use mv squared over r. So L we know is 1000 root 17 lots of g, and we're going to multiply that by the sine of alpha, which is 1 over root 17. You can see what's going to happen there with the square roots. Now the mass is 4,000 kilos. We don't know the velocity. That's what we're trying to work out. And the last thing we need to work out is our radius. So what is the radius that's occurring? Now, we haven't done that, so let's take a moment and let's just think about that for a second. When you read to the question, it tells us that it's flying in a horizontal circular path of radius 32 kilometers. So that's going to be 32,000 meters. And when you work that through, when we work out 1,000 times by 9.8 times by 30,000 divided by 4,000, we get 78,400, and we square root that, and we get a linear velocity, that tangential velocity of 280 meters per second. That's my dog. What's she seen? Is that a postman? Hey. No, just checked. It's a neighbor visiting another neighbor. Anyway, that's question 22. Moving on to question 23. We have an object inside a hollow cone. Now, we need to appreciate that the angle of the cone is 30 degrees in both directions. So that vertical is 30 degrees. You can see it there, just both angles. That's 30 degrees, and also that is 30 degrees. Anyway, we need to appreciate that the inner surface of the cone is rough with a coefficient of friction of 1/8. Now, this is the cone that is rotating about its axis. So imagine that cone spinning really fast. We're told that the angular velocity is 8 radians per second. And there's an object inside that cone that's effectively static. It's sort of held against the side of the cone. I don't know if you've ever seen those sorts of those fairground rides where you're sort of standing inside a cylinder, and basically the cylinder goes faster and faster and faster, and you're pushed up against the side of the cylinder, and eventually the floor disappears from underneath you, and you're stuck against that cylinder. You get the idea, okay? Anyway, so the object is not actually itself moving inside the cone. The cone is what is moving. The object is staying. I know it looks like a ball, and you might think the ball is spinning inside the cone, but the mass, the object that you see as a circle is staying still on that particular point on the cone. The cone is what is rotating around, and as a result, the object goes with it. The thing that's stopping it from moving to some extent is the friction that's occurring on the object from the surface that it's acting against. So imagine that object against the surface of the cone. Its weight is trying to pull it down vertically with its mass is trying to pull it down with a weight of mg. We then have a perpendicular reaction to it being against the surface of the cone, inside surface of the cone. We have friction. Now, we're going to deal with, in the first instance, we don't want the particle to slide down. It's about to slide down, but it's not actually sliding down, okay? So if it's trying to move down, then friction will be acting in the upwards direction, okay? That would be our friction. So we have the reaction perpendicular to the surface, we've got the friction parallel to the surface, and we've got the weight acting vertically down. We know that mu is 1/8 for the friction, and we know that friction is mu multiplied by the normal reaction. So we can say that it's 1/8 of R. So we need to find out a little bit about what the radius of the circular motion is. So a particle of m is placed on the inside of the surface and rotates about with the cone, so that the particle remains at rest relative to the cone. The particle is a distance of L from the vertex of the cone, so that sort of perpendicular length is L, and we want to work out what that distance is, such that the particle is about to slide down, and then we'll look at about to slide up. So bear in mind that depending upon where it is within the cone, if it's towards the top of the cone or to the bottom of the cone, that will have a different radius, and as a result of that, we have a different scenario in terms of the centripetal forces that are acting upon it. So where does it need to be in the cone so that it just stops from sliding down? So if we think about what we have there, we have our radius that we're trying to appreciate. Now, we want everything in terms, we want to find out what L is. So to some extent, I'm best describing everything in terms of L. So my radius is going to be using SOHCAHTOA, sine, cos, tan. Sine is opposite over hypotenuse, so the opposite R is equal to the multiplication of the hypotenuse and the sine of the angle. Okay, now we know what's sine 30, we know the angle is sine 30. Sine 30 is a half, so we end up with L over 2. So the radius is half the that length that we're trying to find out. So if we now start looking at the forces acting vertically, because it's not going up nor down, and so therefore the forces are equaling each other, cancelling each other out, and we appreciate that the angle there is my 30, the angle there is my 30, so we can work on the result, the vertical part of the friction, and we can work out the vertical part of our reaction. So we have the vertical component of the friction is going to be the friction multiplied by cos 30. The vertical component of my R is going to be R sine 30, and that is going to equal to the force acting down, which is the weight of the object, so mg. So we've just worked out that vertical component of R and also the vertical component of the friction. We've got an expression for it. Add it together. So we can insert various things for F, cos 30 and sine 30. And we can sort of simplify it a little bit. That may be of use to us. So R as common factor, we bring 16 out. Which is the 8 and the 2, so I have to multiply R by the R over 2 by 8. Okay, so we have R over 16 brackets root 3 plus 8 is equal to mg. We'll park that for a moment. Now horizontally, we want to deal with the horizontal component of our normal reaction and also the horizontal component of the friction occurring. And that sum total will give us the centripetal force. They're acting in opposite directions. We want sort of the sum net sort of force. So that's going to be its right subtraction. So R cos 30 going to the left, and then minus F sine 30 going to the right. So the difference between those, and that's going to equal mr omega squared. So if we now substitute in everything we have for those various different things, so we've put in a number for cos 30, our expression for the friction, a ratio for sine 30. We don't know what m is, we know what the radius is, it's length divided by 2, and we know we've been told the angular velocity, it is 8 rads per second. So if we now tidy up that as an expression, Again, taking out r and 16 is the denominator factor. We get r of 16 brackets 8 root 3 minus 1 is equal to 64 over 2 lots of ml. And we'll park that as a second equation. So now we can work on both those two equations that we found there. So we've got this one here, and we've got this one here, and we're going to try and work on both of them to get an expression for L. We want to get rid of effectively R. We just want an expression for L, and we can do that if we can rearrange each of those so to be equal to R over 16. That should be easy to do since we have R over 16 as being a factor for both those two expressions. So mg over root 3 over 8 is one expression for r over 16. The other expression from the second equation is going to be 32 ml divided by 8 root 3 minus 1. And we can equal those to each other. And as a result, we can now rearrange that to get L as the subject. We can cancel out the m's because they are the factor on either side. So they cancel out. So we're not concerned with that one. And we get the following. So g multiplied by 8 root 3 minus 1, bring that denominator across, is divided by 32 root 3 plus 8. If we work that out on a calculator, inserting 9.8 in for our value of g, we end up with effectively an answer of 0.4046, something. So 0.40 corrected 2 decimal places. Okay, so that's in meters. So we were looking at a scenario where the particle is just about to slide down. It's at that moment when the friction is just holding it in place from falling down. So now we're going to look at the scenario where it's the other way around. It's about to slide up. So the only difference here is it wants to move up, so the force of the friction is going to act in the opposite direction. It's trying to stop it from sliding up, so it's going in the opposite direction. So it's going to be a very similar process to what we've just done, but the only difference is the force of the friction, both its vertical component and its horizontal component, are acting in a different direction. So the same thing, looking vertically, okay, working vertically, forces up equal forces down. So we have the reaction, the vertical component of the reaction, r sine 30 going up, and the vertical component of the friction, F cos 30 going down, along with the mass creating the weight. We end up with, okay, well sine 30 is a half, so we got the reaction divided by 2. Now remember that the friction is still 1/8 the reaction. Cos 30 is root 3 over 2. And again, we can bring that together as being an expression. We'll bring the r components onto the left-hand side. We end up with, rearranged to be r over 16 multiplied by 8 minus root 3. That's all equal to mg. So just rearranging that second line there. And since our previous part, we can get a sense of where this is going if we just immediately get our rearranged expression for r over 16, because we can have a good guess that the same thing is going to happen this time round. So then horizontally now we can look at the forces acting. So acting towards the center of the rotation, we have the horizontal component of the reaction, which is r cos 30, and we have the horizontal component of the friction, which is F sine 30, and that's going to be the sum total of the centripetal force. So that's going to equal to mr omega squared. Excuse me. So if you fill in what we know there, so we know that cos of 30 is root 3 over 2. We know friction is r over 8. Sine 30 is a half. We don't know what the mass is. We know our radius, it's length divided by 2, and we know our angular velocity, which is 8. So put that in, 8 squared. And again, we're going to rearrange that and factorize it and get it to a point where we've got it equal to r over 16. And we end up with an expression for r over 16 being equal to 32 ml divided by 8 root 3 plus 1. So we have two expressions equal to r over 16. You can get a sense of where this is going. So we're going to equal those to each other. So we end up with mg over 8 minus root 3, and that's equal to 32 ml divided by 8 root 3 plus 1. The m's are going to cancel, and if I rearrange it, I'm going to end up with g multiplied by 8 root 3 plus 1, all divided by 32 brackets 8 minus root 3. And if you bang that out in the calculator, you're going to get a number approximately 0.73. Correct 2 decimal places. So it's a lot further up the cone. In essence, as a result, you can imagine that it's effectively spinning faster. It's spinning around. It has to travel a further distance, and it's just getting to a point where it's just going too fast. In terms of its actual tangential velocity, and it's going to fly out the cone. And as an extra little bit of learning, if you appreciate that, I suppose we said that if it's as long as it's, if you think of the cone, as long as the distance is 0.4 away from its base, and no further than 0.73 from its base, so there's a gap there of 0.33 meters. So if the object is anywhere inside this sort of sweet spot, it's going to stay where it is. If it's too low, it's going to fall down. If it's too high, it's going to spin out. Okay, so you've got that sort of sweet spot where it's fine not to move. And it's independent of its mass. So if you think about the fairground ride, the argument is it doesn't matter how light or heavy the person is, it shouldn't make a difference as long as they're inside that certain sweet spot. They're going to be safe, they're not going to fly out, and nor are they going to fall down inside. So all great maths for if you're designing fairground rides.